Okay, now maybe I can start to talk about this. So this is the overview of this lecture, and the aerosol-cloud interactions still suffer from large uncertainties, and this study will take the investigation into the details of the aerosol-cloud interactions to reduce the uncertainties in the large-scale models and to understand the discrepancies between the model and the observation. This presentation is divided into two parts. The first part is about the cloud indirect effect, that is how the aerosol impacts the radiation by serving as the cloud condensation nuclei. I mainly focus on the regime dependency of the well-known Tommy effect and the relatively less known dispersion effect. The second part is about the impact of the turbulent entrainment mixing on the cloud microphysics. The Tommy effect describes that the increasing aerosol number concentration causes increasing cloud droplet number concentration, which hence reduces the cloud droplet size. The parameter we usually use to gauge the cloud droplet size is the droplet effective radius. This one relates to the liquid water content and the cloud droplet number concentration. Also, this effective radius can be parameterized in the form as shown on the slide. Assuming the constant liquid water content and the beta, the parameters describing the droplet size distribution shape. When we have the increased cloud droplet number concentration, then the effective radius decreases. And then we will have more reflectivities and finally a cooling effect on the planet. The linear relationships between the aerosol number concentration and the cloud droplet number concentration are studied after Tommy's early work. Reuter et al. In 2009 conducted a regime classification showing right figure. Here it is the vertical velocity versus the aerosol number concentration, and the black control lines show the cloud droplet number concentration. They have the blue and the red lines classify the diagram into the three regimes. In the aerosol limited regime, that is the top left part of the figure, the cloud droplet number concentration depends more on aerosols. But in the updraft limited regime, the droplet number concentration depends more on the vertical velocity. The transition regime in the middle shows the highly nonlinear behavior on the vertical velocity and the number concentration. The less known aerosol indirect effect is the dispersion effect. As shown in the last slide, effective radius can be parameterized in the formula shown on the slide. Previous studies show that the shape parameter beta can be calculated by the cloud droplet relative dispersion, which is defined as the ratio of the standard deviation to the mean radius. The increase of the relative dispersion causes increasing of the effective radius, hence less reflectivity and the warming effect on the planet. However, the relationships between aerosol number concentration and the relative dispersion is elusive. Some observations shows positive relationships as the left figure show, but others shows the negative relationship. So the first scientific question this work will answer is whether the regime dependency of dispersion effect help to explain the contrasting dispersion effect. The tool I'm using is a adiabatic cloud Parcel model for the part 1 work. And for people who are not familiar with this kind of model, this is a explicit beam model by calculating the cloud droplet growth by the diffusional growth. And the input of the model is the initial, the temperature, pressure, relative humidity. And we prescribe the dry aerosol size distribution and aerosol hygroscopicity parameter. This one describes how much the aerosol will absorb the water and also the vertical velocity. As a theoretical work, the vertical velocity is prescribed and is constant during this updraft cooling. And the key process this model will simulate is the constant updraft, the delinquencies and the effluences of the aerosols, and also the vapor diffusional growth on the cloud droplet. The output of the model is that we have the cloud microphysics properties, like the supersaturation in the cloud parcel, the droplet number concentration, and the droplet size distribution. Here, the size distribution is represented by the Lagrangian particle bins. So we have the size, concentration, and the chemical composition of the particles for each bin. Here is the result of the regime classification. We conducted thousands of parcel model simulations and with the different vertical velocity and aerosol concentration. The left figure is a reproduction of Reuter's work. Black lines separate the space into the three regimes. The right figure extends the regime classification to consider the cloud droplet relative dispersion. In the aerosol limited regime, the relative dispersion increases with NA, the aerosol number concentration, and decreases with the W, the vertical velocity. While in the updraft limited regime, opposite trends are found. Peak relative dispersion is found in the transitional regime. This finding provides a new understanding to the contrast observations, and this work was published on GIL in 2015. To further understand the regime pattern, 5 vertical velocities from 0.1 to 10 are chosen to investigate the relationship between the microphysical properties and the aerosol number concentration. The cloud droplet number concentration NC increases with NA rapidly when NA is low, but the level off when NA is high. This is similar to some previous studies. The positive relationship between the relative dispersion and NA are found when NA is low, and the negative relationship are found when NA is high. Compared to the droplet number concentration, the regime dependency of relative dispersion is most striking with the non-monotonic behavior and the peak value existing in the transitional regime. So with this feature, we can quantify the transitional regime by the relative dispersion. Here, the vertical axis of this figure is the vertical velocity of the transitional regime, and x-axis is the aerosol number concentration of the transitional regime. The black dots are from the numerical simulations. Red lines is the curve fitting of the blue dots, serving as a quantitative equation marrying the transitional regime, which is located between the 2 black lines defined by the previous work, the Reuter et al. 2009. This equation can be used for parameterization in the future. Now you may have the question why this happens, why the relative dispersion increases when aerosol number concentration is low, but opposite when the NA is high. Here is the explanation. Starting from the condensational growth equation, that is a key equation used in this cloud parcel model to describe the droplet growth of each particle bin. Here, R is the particle radius, and the SP is the parcel supersaturation. SK is the equivalent particle supersaturation close to the droplet that taking care of the curvature effect and the solidity effect from the Kohler theory for the cloud droplet. And G is a function of the temperature and the pressure. Usually these factors influence the DRDT less than the radius and the supersaturation. First, we take the derivative of this DRDT to the radius as the blue arrow shown. There are 2 terms on the right-hand side. For growing cloud droplet, the parcel supersaturation is usually larger than the equivalent particle supersaturation. This one serves as a driving force for the water vapor condensed on the droplet. The first term has a negative contribution to the derivative. The SKDR is usually negative for the cloud droplet. Then the second term has a positive contribution to the derivative. The positive values of this derivative means the larger droplet grows faster than the smaller droplet, then the droplet size distribution is broadened, and the negative values of the derivative means smaller droplet grow faster than the larger droplet, then the droplet size distribution narrows. Here, this figure shows the DRDT versus the droplet radius. The slope of the line on the figure is the derivative as the equation shows. The same vertical velocity, we have the same vertical velocity for the three lines, but the aerosol number concentration is different. The green line corresponds to the aerosol limited regime with small n a, and the red line corresponds to transitional regime, while the blue line corresponds to the updraft limited regime. So we can see in the aerosol limited regime, a larger droplet has a smaller growth rate, and in the updraft limited regime, we see the opposite trends of the lines. The reason for the different signs of this derivative is explained by the right two figures. In the aerosol limited regime, Parcel supersaturation SP is much larger than the SK. Then the first term dominates, while in the updraft limited regime, the second term dominates when the positive derivative is caused. Thus, in aerosol limited regime, when some aerosols retard the growth and the condensational narrowing, the wider side distribution is caused. And in the updraft limited regime, we see the opposite trend. In current many calculations in the models, the droplet equivalent supersaturation is ignored. So the DSKDR is assumed as the zero. This would cause the uncertainties for the simulations when the cases occur in the updraft limited regime. And also, probably like the based on the condensational theory, the side distribution narrows when the droplet grows. But this research shows us in a case when the aerosol number concentration is very high or the vertical velocity is very low, then we have the different behaviors of the droplet population. The results before mainly focus on the maximum supersaturation height that is very close to the cloud base to gauging the droplet activation. However, the further growth of the cloud droplet above the maximum supersaturation height is important for both radiation and also the onset of precipitation. Now, the high dependency of the aerosol-cloud interaction regimes are discussed in the following few slides. These three plots show the mean values of the vertical profile of each property with the ratio of the NA to W in the ranges as shown in the legend. Warm dashed line represents the aerosol limited regime, while cold solid line represents the updraft limited regime, and the black lines is the transitional regime. In aerosol limited regime, the Parcel supersaturation is larger than those in the updraft limited regime for the whole profile. And the droplet number concentration in aerosol limited regime hold almost constant, but decreases in higher levels in the updraft limited regime. Note that most parameterizations assuming droplet concentration is constant during the growth of the cloud parcels, which is not the case for the updraft limited regime. And also the evaporation and deactivation happens in the updraft limited regime. We have a slide later give you more details about this deactivation. The relative dispersion in the bottom left figure decreases with height rapidly in the aerosol limited regime, but the decrease is slower in the updraft limited regime. To further explain the behavior of dispersion, I have the standard deviation and the mean radius here on this slide. We can see the standard deviation decrease with the height in the aerosol limited regime, indicating the narrowing of the droplet size distribution, but the increases with the height in the updraft limited regime. The reason is explained in the previous slide. Due to the difference between the Parcel supersaturation and equilibrium supersaturation. Then the cloud droplet mean radius increases with the height faster in the aerosol limited regime and slower in the updraft limited regime. So here this slide explains the features in the updraft limited regime about the deactivation. This figure is an example of the aerosol limited regime, the top left figure. The black line is the particle equivalent supersaturation of the smallest cloud droplets at the cloud base. And the green circle corresponds to the smallest cloud droplet at about 1 kilometer. In the aerosol limited regime, these two lines collapse each other. So the smallest droplet size at the cloud base is also the smallest at 1 kilometer. But in the example in the updraft limited regime, we see the smallest droplet around the cloud base is as the black line shows. But because the partial supersaturation is only slightly larger than equilibrium supersaturation, this droplet evaporates and deactivates. So the smallest droplet is another one, like the blue line shows. It's a different particle beams. However, the droplet will evaporate if the parcel goes higher because particle equivalent supersaturation is larger than the parcel saturation. The two bottom figures shows the vertical profile of the growth rate in the same particle beams as the top two figures. In the aerosol limited regime, we have larger particle have a smaller growth rate, while in the updraft limited regime, larger particle have a larger growth rate. And this research also shows similar things like this feature is called kinetic mechanism in the Nannis paper in some previous studies. To further see the importance of the equivalent supersaturation in the result, we conducted a sensitivity research. Here we have the DSKDR is assumed as 0 by putting the equivalent supersaturation of each droplet constant as a particular value. Then these 5 figures show the similar properties as we showed before. Although the partial supersaturation in the updraft limited regime is still higher, but the cloud droplet number concentration hold constant for all the regimes. And the dispersion decreases with the height faster also for the other regimes. Then the standard deviation decreases with the height. So that confirms that the equivalent supersaturation is important for the new features in the updraft limited regime. Now here is the summary of the regime dependency of the Aerosol-Cloud interactions. We have the aerosol limited regime as with the features we know before, but in the updraft limited regime, things are different. So in the current planet, when we have the more and more pollution, more and more aerosols, so I think these features need to be taken care in the future parameterizations and the simulation. So what I showed before is the model result. Now I'm showing a simple comparison with some observations to see how this model theory is similar to the observations. Now here are the 186 growing cumulus during a Rakora campaign. This is a campaign sponsored by the Department of Energy in US, and we have the aircraft there to catch the cloud microphysical properties and also some thermodynamic properties of the atmosphere. Here we have taken this growing cumulus, and here I show the profile of the liquid water content, droplet number concentration, and the relative dispersion. The red star is the mean values, and the shading is the ±1 standard deviation. To compare the model with the observation, here we use the perturbed input for the model, and the aerosol is based on the measurements from the 2 instruments, and we do the curve fitting to have this log normal distributions. We perturbed some parameters to have a ensemble simulation. Now this is the comparisons. As before, both the red star and the shading are from the observation. The color dot line is from the car parcel model. We see the liquid water content is at the largest end of the observations. This is expected because we use the adiabatic assumption and the real cloud is not. And we have the perturbed cloud droplet number concentration almost there to cover the range of the observations, but the relative dispersion is smaller than the measurements. This is not too surprising because we have the previous studies saying the entrainment mixing that one breaks the adiabatic assumption, cause the broadening of the cloud droplets. So when we use the adiabatic assumption, this is expected to be smaller than the measurements. Then this comparison motivated me to considering the entrainment mixing in the adiabatic model. Then this move to the second part of the this study. The turbulent entrainment mixing alters the cloud microphysical properties, like the lateral entrainment mixing of shallow cumulus, as the right figure shows in this slide. Now the scientific questions I'm going to answer with some following slides is what are the impacts of the untreated aerosols and the entrainment rate along with the cloud-based aerosol concentration and vertical velocity? How the impact on the cloud microphysical properties. And the second is how the different parameterizations of the entrainment rate of shallow cumulus alter the cloud microphysical properties. This is the cloud Parcel model considering entrainment mixing. The dry air in the aerosols are entrained in the cloud parcel continually at each step. Two parameters are used to represent this process. The first one is entrainment rate, which is defined as the mass fraction of the entrained air. Here, m is the mass of the parcel and z is the height. This parameter represents the intensity of the entrainment. The second parameter represents the entrained aerosols. During the entrainment mixing process, the number concentration of the particles in each particle beam is calculated by this equation. This is derived from the conservation law of the number concentration. And here NAM is the droplet number concentration, and the subscript I means the ice beam. As we mentioned, we use the beam models. Here, lambda is entrainment rate, W is the vertical velocity, and the subscript E means this variable comes from the environment. Here we use the alpha to represent the entrained aerosol. Then in the equation, the entrained parameter alpha is defined as the ratio of the entrained aerosols to the total number aerosol concentration. The physical meaning of this alpha can be understood by these two special examples. When the alpha is 0, that represents no entrained aerosols. Then the right-hand side of the equation only includes the dilution effect during the entrainment mixing. When the alpha is 1, it represents the entrained aerosol balance, the dilution effect, and the particle number concentration does not change with time. These two special cases are used in the previous studies when they want to consider the entrainment mixing. And this brings some limitations to the parameterization. As we say, the supersaturation in the cloud parcel model is very important to see how the cloud droplet grows. In the model, we use the water vapor mixing ratio to represent the moisture, but we still calculate this supersaturation to for us to understand the processes. This equation is shown here. We, after considering the entrainment mixing, we have 3 terms. The first term is AW, is just the updraft cooling. And the second term is the condensation. In the second term, we have 2 terms in the bracket. The first one is the condensation on the pre-existing particles from the cloud base. This one is similar to the adiabatic model. And the expression for this term is shown in the orange box here. Like it is related to the growth rate of each particle beams and the total number concentration for the particle beams. The second term here means the condensation on the entrained aerosols. Here we have the lambda entrainment rate here and the entrained aerosol here to represent this term. And the third term is the mixing for the temperature and the water vapor. We have this PE is the temperature from the environment, and the QVE is the water vapor mixing ratio from the environment. Now I show the supersaturation on the left side to show how this variable depends on the alpha and the lambda. When we have the lambda is 0, alpha and lambda is 0, as the black line show here, the equation drops to the adiabatic version with the maximum supersaturation close to the cloud base, then decreases with the height. But when we have the entrainment rate larger than 0, we have the supersaturation increases with the height in the higher levels. That's because during the dilution effect, this NAM is smaller and smaller with the height, then the condensation term is relatively weak. So when the sink term is like weak, so then we have the source term relatively dominant, then we have these increases with height. But when we have the alpha go from 0 to the larger values, we see that these increases with the height relatively disappear until it decreases with the height when alpha is 2. So then this feature tells us we need to both consider these two parameters to see how the supersaturation change with the height. Now I'm showing how the impact of the lambda alpha together and also with NA on the supersaturation in the NC. First, the top row shows the supersaturation. The first figure shows lambda is 0. The solid and the dashed lines are from two cases. The solid line is from clean case. The dashed line is for the polluted case. When the lambda is constant, as we show in the previous slide, we have the supersaturation either increases with height or decreases with height, depending on the different alpha values. And now we also want to have the lambda change with the other variables, because in the previous studies, this one is not a constant value. We use two ways. Based on Gregory's work, they have the theoretically derived lambda based on the buoyancy and the vertical velocity. And also we have another study from this is a fitting or derived from the aircraft environment. Then they have a different formulas to calculate the lambda. We see the supersaturation profiles are different from these two studies. When we use this from the aircraft, we see this increases with height. But when we use this one, we have the basic shape is similar to the adiabatic assumptions, but the values are different when we have the different in-sheet aerosols. When the supersaturation is different, it is not surprising the droplet number concentration is different. So this is for the with other factors are the similar, only by varying the in-sheet aerosols, we have the droplet number concentration lines quite different for the different cases. Also, we see the relative dispersion in these bottom lines. The most striking feature is the increases of this relative dispersion here. That is because when we have the larger supersaturation, then the smaller aerosols are activated. This is kind of the secondary activation. So we have this jump of the relative dispersion to the larger values. This is a summary of the second part. We have the newly introduced parameter alpha that can represent the effects of in-sheet aerosols. So the nonlinear relationship between the in-sheet aerosol entrainment rate and the cloud microphysical studies are shown before. And also the treatment of the entrainment rate and the vertical velocity in the cloud parcel model impact the profiles of the microphysical properties. Part of this work has been published in the GRL paper, and the other are still in preparation for another articles. I don't include the detailed derivatives in this presentation in case this goes too long, but if you have any questions, I'm happy to answer. Thank you.
So thanks a lot, Jingji, for your presentation. It is very for me, it was really very interesting. So I must say, I'm not a warm cloud physicist. I'm a little bit overwhelmed of it.
Oh,
But this
I'm
is not
sorry.
this is of me because I'm an ice person, and
Oh,
yeah, I know something a bit about warm clouds also, but not in the detail that you presented it. Anyhow, I liked it a lot, and I open the floor for questions now. So, who wants to ask something? Please raise a hand here in the reactions button. So I don't see a hand. But then I would like to ask you to go back to your first summary and maybe,
okay. Here it is.
yeah. So this was, for me, it was a little bit too fast.
Oh.
Yeah. I don't know what the others, but if nobody asks, then I can ask my stupid questions.
Oh, no. I'm sorry.
No. Everything's fine. It's so, but I'm not an expert here. So I think, and I also would encourage others who are not that deeply in warm cloud microphysics to ask stupid questions. um, Yes, so we have this nice diagram. So I understand aerosol number concentration versus vertical velocity, and there you have the updraft limited regime. So that means if the updraft is low, then the what does it mean? If the updraft is low, then the cloud drop number depends on the more on the aerosol concentration, and it stays low.
Yes. When the
It's
when the up no when the updraft velocity is low, the cloud droplet number concentration is more depend on the updraft velocity. Like if
okay.
we change the vertical velocity, the number concentration changes a lot.
And the aerosol limited regime, so that means if there are not many aerosols, then not many cloud droplets can appear, even if the updraft is high.
Yeah, yeah, right.
Yeah.
Then the cloud droplet number concentration change
Mhm.
more with the aerosol number concentration.
Yeah.
It's more sensitive to the aerosol number concentration. Yeah.
Yes, and but here you have now several points.
Yeah. Usually the first points in the updraft and the aerosol limiting regime tell us about the supersaturation. We know that when the supersaturation is like mirrors the water vapor pressure, like if it's high, then the water vapor is more likely to condense on the
Mhm.
droplets. So this is
Mhm.
have the different supersaturation for the different regime. It's usually corresponded to the activation fraction. That
Yeah.
parameter used a lot in the climate models. The second bullet term is like the relationship, whether the cloud droplet number concentration depends on aerosols or vertical velocity. That's different for these two regimes. The third one is this relative dispersion. It measures the droplet size shape, how wide of the shape is or how narrow it is.
Yeah.
And
So this
this one, yeah,
I
this
understand.
one.
I understand the
Mhm.
first points for the two regimes. So this the dispersion. Yeah. Sorry to ask.
No.
It's positive for the aerosol limited regime and negative for the updraft limited regime, and it means the change of shape of the cloud
Yeah.
droplet price distribution. But what does it mean if it's positive or negative?
When this is positive, that means when we have more aerosols, when we have more pollution, the size distribution becomes wider.
Ah, okay.
Yeah,
Ah,
and yeah,
it's the width of the
yeah,
okay.
yeah, yeah, because the width is related to the effective radius that will finally impact the radiation effect of the cloud.
Mm-hmm. Okay.
And yeah, and the fourth bullet is we know the condensational narrowing maybe from our like microphysics class, like when the large droplets grow uh, slower and smaller droplets grow quicker, then the droplet
Mm-hmm.
is narrowing with the height. But in the updraft limiting regime, it's different. It's broadening. This one is now talked a lot in the previous studies. And the last bullet is majorly related to the parameterization because usually we assume the droplet number concentration is constant. Then we use the constant values in the climate models. But this research shows when the situation is in the updraft limited regime, we have the deactivation. The activated particles can be deactivated back to the aerosols in the higher levels in this updraft limited regime.
Okay. Yeah, thanks a lot for this extra explanation. Really, it helps me to understand better. And while we were talking, there people started to write in the chat. So we have a first question here by Mahen Konvar. And first, so he mentions great talk. And then he asks if these three regimes have dependency on the distance from the cloud base?
This regime is gauged as close to the cloud base, that is the maximum supersaturation height. And it is more close to the cloud base, more close to the lower levels of the cloud, then this regime dependency may be more evident because when you go higher, when the ring starts, then the whole stories could be different.
Maren, does that answer your question? You can switch on your microphone if you want. And
yeah.
oh, he says thanks.
Yes,
He
thank
wrote.
you. Yes, yes. Yeah, thank you. Yeah, I think there will be some other processes maybe depend. I mean, it will be effective like coalescence. Yeah,
Yes.
yeah. Thank you. Yeah. So it is more pertinent near to the cloud base.
Yes, this is more related to the droplet activation. When if we goes higher, when we have the collision coalescence, then the story is changed. Also, if we goes higher, we have the entrainment mixing, we have the dry airs intrude in, then the stories could be different.
Yeah. Thank you.
Yeah, then we have a question here from Heike Wex, and because she types in her question because her camera and microphone doesn't work and properly. So here is the question, is about the effect of clouds on climate. Do you have an idea how real clouds might react in a future warmer climate compared to what is obtained by models now?
In my research, I like in the future climate, we mostly focus the pollution, the aerosol number concentration. We don't do many work about the warming things. When we have more pollution, when we have more aerosols there, the clouds usually behaves different. Like they can, as the like previous, the Thomas effect said, the clouds may have the smaller droplet reflect more on the cooling effect. But this cooling effect is sometimes like overestimated by current climate and cloud models. One possible explanations of this overestimation from our models is like we miss some physics there, we miss some processes there. here, this research is like one possibility. It's like when we may not consider the updraft limited regime, the behavior is there. In the future, when we have considered more physics there, more processes there, I think the climate models can estimate what happens with the cloud microphysics and the radiation better.
Then I have a follow-on question, but do you really think that the pollution with aerosols will keep on increasing? Because from what I know, in comparison to 20 years ago or so, then the aerosol pollution is decreasing. So at least in the highly industrialized countries, not in Asia and yeah, I don't know the proper English word for that, in the newly developing countries.
Yeah, since the aerosol number concentration is highly like different in different countries, different continents. So generally speaking, I don't hope the pollution is worse in the future. And yeah, but this research just provide a quantification. What would happen if we have more? It provides us the understanding, the knowledge, and what will happen in the future planet there.
Okay, thanks. And also Heike, she said thanks in the chat. Are there more questions? So this does not seem to be the case, and so I thank you again for your nice talk. What I like here in the ICCP Journal Club is the diversity of talks. It's all about clouds, but the topics are really different. And yeah, but that's why we started the Journal Club. And so our next speaker in 4 weeks will be Sylvia Sullivan. And Sylvia, she will talk about something completely different. Then we move to ice clouds and two perspectives. So the title is Two Perspectives of Ice Microphysical Impact on Cloud Radiative Heating. Yeah, we look forward to this. And I think for today, if Audron, are you there?
Yes, I'm here. Yes.
Yeah, if you don't have anything to mention now, I think we can close for today. Can we? Or have I forgotten something?
Yeah, I think we can let some extra time if people want to discuss, but we can conclude officially and see.
Yeah, we could keep on discussing, but if there are no further questions, then we also might close for today.
Great. Why not?
Yeah, and thanks also to the audience for being here. Hope to see you again. Okay, bye.